give you homework today.
Okay, that's not.
I don't know.
So, okay, today we have a few notes I'd like to cover. Take a seat.
Oh shit, the camera's on?
Yeah, I am. I got your dad.
Is that homework due today?
Sorry, dude, I forgot the camera was on.
What?
Is that homework due today?
Yes, we have homework due today. We'll get to that at the very end if you want to turn in at the end of class. That's fine. Okay, let's take notes. Go sit. Grab a calculator.
Mr. Ward, I'm not a dog.
Okay. All right.
Hey, let's see, read to Brennan.
Yes.
Thanks.
Mr. Ward.
Slowly proving we can't have an open senior info. So, today, what we're going to be covering the logarithms, but we have to go through a couple properties today to make sure that you understand it. The first thing I want to make sure of, let's do a couple of properties with multiplying, dividing, and adding and subtracting today. Those product and quotient rules. That way we can understand the concepts of why we're doing it. And then we're going to get to a problem where you have to use it. Okay? So we're going to kind of ramp ourselves up into difficulty. The goal today is we're going to end with, we're going to look at natural numbers, like the natural number e. And then we're going to look at like where that come from, why is it a thing, why do we do logarithms for it. That's what we're looking at, okay? Now, first step here. I want to talk about some of these basic properties. So like 5 to the x, and let's talk about if this equals a number. Say like 25. The idea of what we're doing today is trying to solve for like x's, right? That you can either, number one, guess the number, or number two, you can do a logarithm that will give you that answer, right? Because, yeah, we know this number, right? So 5 to the second power is 25, because what this literally means is 5 times itself, right? That's what gives you 25. Now, those are easy numbers. There's two ways to think about that problem. You can, number one, literally guess numbers until you get there, or just think about that the 25 is a change of base. Right? This is something we talked about last year a little bit, is that 25 is 5 times 5. Right? And that tells you how many numbers you have. And so you can literally guess at what that would need to be. Well, there's two bases. Right? You can break it down to prime numbers. Now that might work, that may not. Like what I mean by that is if you had a problem like this. 2 to the x equals a 32, right? You could guess the number. You could guess that it's a 5. That will give you that. Or you could try to break this down as far as you can into prime numbers. Well, that's 2 and 16. 16 breaks down to 2 and 8. 8 breaks down to 2 and 4. 4 breaks down to 2 and 2. And so your prime factorization, the thing they teach you in like elementary days and junior high days, is that the prime factorization is literally 2 times 2 times 2 times 2 times 2, right? There's 5 2's there. And so your answer is this number that goes here is a 5.
I remember that.
Yeah,
Is that why we did that?
Yeah, that's why.
Oh.
And now this is
A long time ago, right? That was like a purpose of doing it. Now, you're probably thinking, okay, I remember like talking about greatest common factors and other things, but there was a reason why they taught you that strategy, is because once I'm doing that problem, I can figure out, is it going to be a nice clean number, or is it going to be a weird decimal, like an irrational number? Because at some point, you're going to eventually get to this. 3 to the x equals 8. No longer a nice number anymore. Because if you try to do the prime factorization of 8, that's 2 times 2 times 2, right? That's breaking down 2 as far as you can. There's no way that I can figure out this power without doing a logarithm now. Because these are not 3's. They're not 3's, they're 2's. So I can guarantee that this number right here is going to be a crazy irrational number now. Does that make sense why we did prime factorization? You're either trying to figure out like how many there are total, or it can immediately tell you that you don't have a nice clean number. That's why that prime factorization comes in. Okay, now, here's the idea. To solve this problem, that's what we were starting yesterday. We were talking about like the concept of like what we do. So, let's review that, and then we're going to get into some of those properties here. So on this problem, what you do, since these are both numbers, is you could take the log of both sides. That's one method. Take the log of both sides, okay? That's one strategy you can do. So that's log of 3. You can drop the power out front. That's being multiplied out front. And then this is log of 8 on this side. And then the step is, since these are being multiplied, you divide the log 3 across. So this would be x equals log 8 divided by log 3. Questions at all about that? Now, some people like that, some people don't. Because I've told you a different strategy for doing this problem earlier. Last year, in fact. That when you had a problem like this, you could change this from exponential form directly to logarithmic. If there's only one side that has the power, it's called that circle method. That you go log of whatever your base is, of this other number equals the power, because the logarithm equals the power on your base. And so what you're looking at here is something that some people have the luxury of typing in their calculator. It's the same thing as this, because how you actually type this in a calculator, for most people's calculators, is you actually have to type it like that, where the 3 falls out the bottom and becomes its own logarithm.
How do you solve that without a calculator?
What?
How do you solve that without a calculator?
So that's where the other property comes in. So that's where like multiplying and dividing would come in. So if we looked at those numbers we did yesterday, right, where I had 2 and 3 on the board, right, and maybe I had that answer to you.
Wait, would you subtract these though, or what?
So that, we'll look at that separate strategy. So let's take a look at that here in a second. So, all right, is there any questions with the 7? I'm gonna get to that answer. I'm gonna get to it here in a
Are we
second.
subtracting now, or are we adding?
We're gonna be adding, eventually. Oh,
If it's
this,
dividing?
oh,
Oh, never
it's
mind.
when I change. This is different. This is different than, adding and subtracting it.
Whatever.
Okay, we're dividing that. Okay, questions on the 7s? Does that make sense, the idea of logs? Okay, let's get to those properties now. Those properties I introduced yesterday. All right. We learned 3 properties yesterday, I should say. This was one of the properties we talked about how to drop powers down. This is the power rule. One of the other properties we talked about is if they're being multiplied on the inside of a logarithm, like that, you can separate them into their own logarithms, and they'd be added together. That is something we are going to use here in a minute. I'll show you the reason why we do that. Next is if they're being divided in one logarithm. M divided by n. You could write these in their own individual logarithms and subtract them. Now, here's the thing.
See, that's what I meant right there.
Yeah. This, what I have written there, is very different than this. Because these are 2 separate logarithms being divided. That is one logarithm where the things inside the parentheses are being divided. There's a difference between this setup, like written like that, versus written like this. You see that?
When do we ever divide
Okay.
inside the log?
So 2 numbers on the inside, we'll talk about it here in a second. That's the goal today, is to look at some examples of like multiplying and dividing, where we actually see something like that. Okay. Questions at all about the properties up to this point? Okay, my goal today is to do about 3 examples, now that we've talked about the properties here. 3 examples, one of which we're going to talk about like, why would this even come in? Like, why would we do something like these? Second thing we'll talk about is the natural number, and then the third one we'll kind of use an example of it. So, I'll jump right in the deep end here. Five, x plus 2, 10, 2x minus 1. All right. This problem, I'd like you to have somewhere in your notes. This is one of the homework problems, or it's really close to homework problems, not the exact numbers. But this is something that you're going to be requested to calculate. I do not want this typed into calculator. I want the exact answer for it. This is kind of mixing everything up to this point together. It's going to require that you know how to distribute, how to do the power rule, what product rule means, and all that stuff.
If I take this into
Eventually I could type it in, but not right where it sits. I don't know of a calculator that could do this. I didn't even know if that 2.8, that platinum, like, that platinum 89 edition by Texas, I don't even know if it could solve this.
Big demos.
Desmos, you can draft it.
So you're telling me that $281 just like type in and say software?
I don't know if it could handle this one just because of the level of work and like what you'd have to do. I don't know what they have it pre-programmed to do. I don't know if it can just do algebra 1 or if it can actually handle calculus. So I don't know. Maybe probably good. I
What
don't know.
about Wolfram Alpha?
Yeah, they could do it.
They could solve it.
All right. Now let's walk through this concept. What I would do first. Do you agree that these are both numbers on the basis?
Yeah.
Okay, so I'm going to take
Yes.
a log of both sides. I'm going to stick with that method I just did a little bit ago. Log 5x plus 2, log 10, 2x minus 1. Now, why I'm writing it like this is why I'm doing the log of both sides. These are whole numbers. They're not natural numbers. So, the natural number, I should say. What I'm going to do is I'm going to take the log of both sides, and what will happen here is the powers will drop out front. So this x plus 2, that's in parentheses here, is going to drop out front. And same with this 2x minus 1, that's going to drop out here as well. So here's what we have. X plus 2, in parentheses, log 5. 2x minus 1, in parentheses, log 10. So it's just being multiplied on the front. Now, do you agree that there's x's on both sides of the equal sign here?
Yep.
And I can't just solve this. I can't just, just simply drag x's around because they're in parentheses. So what I actually have to do is I have to distribute this log 5 into this parenthesis. And I have to distribute this log 10 into this parenthesis because it is an actual number.
So doesn't that cancel out?
Yeah, we'll talk about that. That's why I did it. So you'd have to distribute it in. Now, that's if there's weird numbers, but you guys already said, what is log 10?
1.
To 1, so it's a nice number. So that's why I picked it. Questions?
No, I'm just hitting the stop work.
Let's write that down. Now, if that was like a log 7, yeah, you have to distribute. But you guys already recognize log 10 will disappear. Okay, log 10 is a 1. So since this is the number 1, just this part right here, it basically can go away, and so I'm just left with 2x minus 1. So it's kind of nice that we have that written like that. On the other side, I do have to actually distribute. So I actually have x times log 5. You could divide it over, but I wouldn't because there's an x on the other side, so you have to distribute first. So plus 2 log 5. If there wasn't x's over there, yeah, I would divide it over. Okay, understand how I distributed the log 5 through the parentheses. Okay, so now what I'm going to do next, I'm going to drag all the x's to one side. So if it has an x, it's going over. So you have to add and subtract things across the equal sign. So here's where I'm at. I'm at what? X log 5. Those are multiplied together. I'm going to subtract the 2x across. I'm going to subtract the, what is that, 2 log 5 across? So that's bringing this 2 log 5 over and bringing this 2x over. That was a negative one. I got the negative sign on the wall. There.
Wait.
Okay, I'll stop and let you get kind of caught up and kind of see what I did there.
Why'd you do that for?
Why did I do what? Why did I drag things around?
Yeah.
I want to get x's to one side. I'm still solving for x, right? There's multiple x's. It's like a algebra 1 problem where you have to get all the x's to like the left side, all the numbers to the right side.
Alright.
Okay, we're good so far?
Yeah.
Next step, I'm going to factor out the x, because this side, both items have x's in them. And they're not like terms, I can't just subtract these. That's a weird decimal, and that's a number 2. Like this is irrational, I can't just write the decimal and then subtract 2 off of it. So to get the exact answer, I'm gonna factor out one of the x's out of both. So if I factor out an x, that's what I'm left with on that side, right? Because each of them had x, I'm pulling the x out front. Back here, I have the 1 minus the 2 log 5. So remember, when you factor, you're taking out the common idea, you're taking out the x. And the last step is divide your answer over. So divide this digit, whatever this is, you're dividing that over to the other side, because these are being multiplied together. So your final answer is this. It's -1 minus 2 log 5, and that's all being divided by log 5 minus 2.
Is there a shortcut for this?
No, you just did it.
That was a shortcut?
Yep. That was literally the shortcut using
Line
properties.
goes.
So how long's the long cut?
Hard enough, I don't want to do it.
What do you do differently?
Calculate numbers and digits and set, like substitute in other letters. I don't want to.
But you know how?
Yeah, I've done it before and I don't want to ever do it again. So, all right.
You should teach us quick. How long would it
Okay,
take?
all right.
What's the last period?
Questions? Take us a while. All right. Questions on the concept of what I just did there?
No.
Okay.
So wait,
Now-
you just leave it at that?
Yeah, that's the exact answer for x. That would actually represent a number that I could plug into both x's here, and it would make the left side equal the right side. Like that's the concept.
But can I get a decimal from this bad boy?
You could get a decimal. You could take that decimal, plug it back in here and here, and actually see that it would balance out the right left
Oh, we
side.
have to type it out.
It's
Hold on.
happening.
Okay.
Would it be possible, like, at the very beginning, change the base?
If they had the same bases, yes. And that's the thing I was going to bring up. Like, what happens when you could make these the same bases? Then the problem's way easier. Like, this is like overboard. This is one of the problems I saw in the book where you couldn't change the base, right? There was one problem that I saw where they did the thing with the 32,
485.
where they did something like this. It was like 2 to the 3x plus 1, and on this side they had 32, and it was x minus 7. I think that was the number that they had. And so, this problem, instead of doing it like this, where I take the log of all sides, if you recognize that they have the same base, like this 32 is the same base. I can make this 2 to the 5th power. Now this problem just became significantly easier. Because now that they have the same base, I can now just set the powers equal to each other. Now to do that problem, I'll have to take the 5 times this thing. So I have 2 to the 5x minus 35. And on the other side I have 2 to the 3x plus 1. Because that's a law of exponent, you can just multiply the powers together. And now that they have the same 2's, you can now cancel the 2's out, and you're just often going with the power. 3x plus 1 equals 5x minus 35. So do this problem, so since the 2's cancel out, they have the same base, I don't need to take the log of all sides, just the power should be the same, that makes the left and right side equal. I would subtract the 5x across, subtract the 1 over, so this is a negative 36, this is a negative 2, and your x ends up being an 18. And that's what makes both sides balanced. Questions at all about the concept? That's why I brought up that one primarily. All right, the last thing I want to talk about today is the natural number. The final thing is like, where's the natural number come from? Why do we have its own logarithm? That type of thing. Natural number, e to some power, right? Well, if I put e to the first power, it's like 2.71 blah, 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 blah. There's a bunch of numbers across the screen. Where this comes from, it comes from the compound interest formula where things grow at a constant rate. If you don't know what the compound interest formula is in math class, we did it in pre-calc, I think a little bit in that 1/3 chapter. where you have some principal amount of money that you're investing. You have 100% plus the rate divided by how many times they compound it. The compound times the number of years. This formula is the compound interest. So you have your rate for your bank account, like a student loan or a credit card. You divide by how many times they compound, how many times they charge you an interest per year. Most credit cards and student loans charge you 12 times a year if you don't pay it off. That's where they get a bunch of money from it. And so how they made this turn into like E is they did this. First step is they made this a fraction by doing the reciprocal, moving the R to the bottom and writing it like this. There's a reason why they did that. Up here in the power, here's the thing. If I multiplied by an R on the top, would you agree that that would change the entire problem?
Yes.
But what if I divided by an R?
Like that?
Like-
How would this be times 1?
It'd be times 1. Do you agree with that?
Yes.
Yes,
Okay,
sir.
so I'm going to rearrange. What if I did this?
No,
Would it
that's,
be different or is that the same?
that's the same.
That's the same, right? Because the n would be taken times RT, and if you divide by R, the R's would still cancel out and be still an NT. Now, why they did this? What if I wrote it like this?
That's different now.
No, it's not.
Yeah, it is.
Because it's a law of exponent. That when you multiply by a power, the powers would multiply together, and the R's would still cancel out. It's still the same problem. So, now, there's a whole reason why they're doing this.
All
right.
You need a signature like phrase that you say every time you
Nope,
certifies.
just the camera stops after like 20 seconds.
You know what I mean though, right?
Okay,
You don't say like welcome back.
Like,
go. All right, subscribe and
like
like.
this word,
All right, but hey, what they do is they substitute out the n over r. The reason why they wrote it like this, why they put the little extra r in the power, is because if you recognize they have the same variables here and here, and they pick a new letter to substitute in there for n over r. I think they use the number or the variable h for n divided by r. And so they substitute that in, and so here's what we have. We have 1 plus 1 over h to the h power, and then that's all to the RT, right? Because h was n over r. And now why they did this is if you start typing this in a calculator, and you start typing in bigger and bigger numbers for h, it doesn't matter if h is a fraction. If you just type in bigger and bigger numbers in for h, so if I did like 1 plus 1 over 1,000, and I put that to the 1,000 power, okay, and I don't care that there was an RT out here and there was a P here, but if I type in bigger and bigger numbers for R over N, and this is my H number, if I type in bigger and bigger numbers, this number every single time will turn out to be 2.71 blah, 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 blah. It actually ends up being the natural number. The bigger and bigger these numbers get. And so the idea is that what they do is they substitute out this whole thing here. They take out that whole box and they just write the number E for it's growing exponentially. So P, they replace that whole box with E, the RT. And this is the formula that we were using like 2 or 3 days ago in here. That this formula is the continuous growth problem.
he's right.
And so the idea is that this is P equals R to the T. The principal amount that you're investing, it's growing exponentially or continuously. It's growing at a certain rate, a K value, for some time.
That's wild.
This is groundbreaking.
So why they created this is because they started noticing that it didn't matter what the problem was. If it was growing exponentially, you could change a problem from something like this, where it's like 2 to some number. You could change it to an E every time, exponential growth, and all the only things that would change would be these two numbers. So that's why in the homework we did a couple like sections ago, where you were trying to figure out like growth rate and time that was involved, or just like identify those parts, is because they were getting you used to seeing these formulas over and over and over, because it's the same formula, it's just written differently. It's either, continued or constant growth, or it's continuous growth. but they're related to each other. And it was one of those things like once you see it, now you understand why they have a natural log and why they have a log is because they just have different values, even though they'll give you the same result on the calculator. So it's kind of weird when you start to see how all this stuff is like interconnected and how they're all the same kind of formulas. They just have different looks to it. So kind of cool looking. But that's all I want to talk about today. So on intro E, where it comes from, we're going to talk about the natural numbers and how to do all these properties with natural numbers on Monday. Questions?
So that's like, you said human population grows by that?
Yeah, everything does. Bacteria, like it's so weird.
It's so confusing to me.